All right, let's jump right into this explainer and build a conceptual mind map that connects the totally invisible microscopic world to the everyday things we can actually see and feel. Today, we're exploring one of the most fascinating, foundational concepts in physics, the kinetic theory of gases. We are going to take a journey from the unimaginably small and chaotic all the way up to the physical forces that literally govern our reality. To start us off, I want you to picture something super simple. Just think about a standard inflated balloon. Now, obviously, we all know there's air inside of it, but let's zoom in a million times. What does that actually look like? And how do those tiny pieces behave? It's absolutely not just a static, boring cloud of stuff in there. It's actually this bustling, high-speed metropolis of invisible particles. But to truly understand what's happening, we need a framework. So, to map this all out today, here's our agenda. 1. The invisible world inside. 2. 6 rules of ideal gases. 3. The origins of gas pressure. 4. Temperature and kinetic energy. And 5. The mean free path. Let's start right at the very root of our mind map. Section 1. The invisible world inside. Defining the theory. Basically, this theory tells us exactly what a gas is made of, which is tiny atoms or molecules, and how those microscopic pieces are constantly moving around. You know, the word kinetic literally just means motion. So instead of looking at gas as just empty space or some generic fluid, this theory describes it through its molecular composition and the relentless, non-stop movement of those molecules. It takes the totally invisible air around us and gives it structure, rules, and a really solid mathematical foundation. Now, to keep things simple, scientists use an ideal gas as a theoretical model. Unlike the messy reality of everyday real gases, an ideal gas is made of tiny point particles with perfectly elastic collisions. It's a flawless mathematical construct. But here is the secret. Real gases can actually act like this perfect ideal model, but only under specific conditions, specifically when they are at a very low pressure and high temperature. Moving on to the main branches of our map. Section 2, 6 rules of ideal gases, the microscopic laws. Okay, here are the first 3 rules. First, gases are made of a vast number of incredibly tiny spheres zooming around, which we call point particles. Second, they are in constant, rapid motion in completely random directions. There's no traffic cop down there, it is total chaos. And third, when they hit something, they bounce back perfectly without losing any energy. Think of it just like a brand new, ultra-bouncy tennis ball hitting a concrete wall and rebounding with the exact same speed. That's what we call a perfectly elastic collision. Now, when I say a vast number, I really want to give you a true sense of the scale here. 10 to the power of 20. To put that into perspective, a simple 1 centimeter cube of air, so something smaller than a sugar cube, can contain 10 to the power of 20 molecules. That's a 1 followed by 20 zeros. It is an almost incomprehensible swarm of activity happening in the empty space right in front of your nose. Let's round out the final 3 rules. Fourth, these particles mostly just ignore each other. There are 0 forces of attraction or repulsion pulling them together or pushing them apart, until the exact fraction of a second they physically crash into one another. Fifth, their average kinetic energy depends strictly on the temperature. Basically, they speed up when heated. And sixth, this brilliantly illustrates the nature of matter. If you were to squish all those billions of particles together, their actual physical volume is totally negligible compared to the massive amount of empty space around them. Honestly, a gas is mostly just pure emptiness. So how do all these invisible rules create something massive that we feel every single day? Let's shift to Section 3, the origins of gas pressure, from micro to macro. Pressure isn't magic, right? It's just a simple 3-step physical process. Step 1, the particles move constantly and randomly. Step 2, because they're moving so much, they repeatedly collide with the walls of whatever container they're in. And step 3, while one single microscopic impact is practically nothing, when you have billions upon billions of these invisible particles constantly slamming against the walls every fraction of a second, they apply a collective force over that area. And force divided by area, that is exactly what generates macroscopic pressure. This actually brings us to a fascinating real-world question that connects those physical strikes against a container wall to the weather outside. Why do car tires sometimes just randomly burst in the heat of the summer? To answer this, we have to connect pressure with another major concept. Let's zoom out to another branch on our map. Section 4, temperature and kinetic energy, heating things up. It all boils down to this. Temperature is directly proportional to average kinetic energy. If you add heat, the particles move faster. It's a direct, undeniable link. And this perfectly illustrates our tire question. The intense summer heat increases the temperature of the air inside the tire. That heat energy translates directly into kinetic energy, making the internal particles move incredibly fast. And because they're moving faster, they strike the rubber walls of the tire much more frequently and with much more violent force. This massive increase in microscopic impacts raises the macroscopic pressure to the point where the tire just can't hold it anymore, and boom, it bursts. This chaotic, rapid motion also drives what physicists call transport properties. As these particles zip around, they carry things with them. In viscosity, they transport momentum, which causes fluid friction. In thermal conductivity, they transport heat from one place to another. And diffusion? Well, that's a transport of mass. This is exactly why if you open a bottle of perfume in the far corner of a room, those perfume molecules get carried by the chaotic collisions of the air, spreading out through diffusion until just moments later you can smell it everywhere. Finally, let's zoom all the way in for our last section to look at the actual journey of a single particle. Section 5, the mean free path, life between collisions. We call this specific journey the mean free path, which is just the average distance a moving particle covers before it collides with another one. Remember how we said there are 10 to the 20th molecules in a tiny cube? Because it's so incredibly crowded, a single molecule can only travel a very short average distance in a straight line before it physically smashes into a neighbor. It's honestly like trying to sprint in a straight line through a packed concert crowd. You are just not going to get very far before bumping into someone. And what happens when they bump? A continuous, endless cycle of momentum and energy exchange. Every single collision completely alters the particle's path, its speed, and its momentum. One particle might speed up while the other slows down. They bounce off, travel their incredibly short mean free path, and then boom, they hit another one. It means the microscopic world is in a constant, relentless, never-ending state of dynamic exchange. So as we wrap up our conceptual mind map today, I want you to consider this. If the solid physical forces we feel every day, like the air rushing past your face or the pressure in a tire, are actually just the macroscopic illusions created by billions of invisible, chaotic, microscopic collisions, what else are we looking at in our universe without truly seeing? It really makes you stop and wonder about the hidden architecture of everything around us, doesn't it? Thank you so much for joining me in this explainer today. Keep questioning the world around you, and I'll catch you on the next one.